Okay, so this chapter 12, and it's it's going to be a very short chapter where we're gonna be talking about sequences, two different types of sequences, um, arithmetic arithmetic sequences and geometric sequences, and also we will cover a little bit of geometric series. Um, Also, we would go over the binomial theorem. So let's go ahead and define what is a sequence. Or a sequence is a function. A sequence is a function whose domain is a set of positive integers and whose range is a subset of real numbers. So the domain is going to be only positive integers when talking about a sequence. For a sequence, the domain is always going to be positive and integers. Here's an example here. So we said it's a function. So you see, if you have a function f of x equals 1 over x, if you graph it, it will be the line, this line, all the way through. And it's a continuous graph. But for a sequence, it's not going to be a continuous graph because you only will consider for the domain integers only. So that's why it's going to give you the value for x equals 1 for, so basically it's n, um I, and for the function, actual function, it's a um, continuous function. You call it x, and for the sequence, you're gonna call the independent variable n, where you're going to count only the numbers that are positive and integers, positive and integers. So at this point, you see you're gonna evaluate for for n equals 1, for n equals 2, for n equals 3, 4, and so on. And you can graph it, but it's going to be some dots for each value of n. And whatever you can get some negative value when you plug in the value n. You can find positive values. We can use it. But only thing that you need to know is that when you're working with sequences, the input must be a positive integer. So here's an example here. We have this sequence, and that's pretty much how they're gonna denote the sequences. They're not going to put f of n just like we do for a regular function, because it's going to be a set of value. Then we're gonna use this notation of um, a with the n like this, and you can put it in braces to imply that this is uh, a set of values. So you're gonna find a n for each value of n. So here, the question they ask me, they say they defined the sequence an as n minus 1 over n. And then they say that we need to find several values for the first six values, the list the first six terms of the sequence an. So what you would do is you're going to find the first values. But now, um, the first six values, it depends on how you start, right? So if you start with 0, then you cannot have a value because n cannot take the value 0. So your sequence cannot start at n equals 0. Just like we had here, we could not start with n equals 0 given n is in denominator, and once it takes the value 0, then it would not be uh, a value that defines. So that's why you need to start with n equals 1 to find the value. So we're gonna find a1. Everyone understands why we cannot start with 0, because 0 is an excluded value because it makes the denominator equal 0. A1 equals 1 minus 1 over 1, so that's 0 over 1. So a1 equals 0. A2 equals 2 minus 1 over 2. A2 equals 1 half. A3 equals 3 minus 1 over 3. That equals 2/3. A4 is 4 minus 1 over 3 over 4. So that's 3 over 4. A5, 5 minus 1 over 5. So 4 over 5. And last, A5, A6 equals A6 equals 6 minus 1 over 6, so that equals 5 over 6. So just plug in. List the first several values, several terms of a sequence. Over here it says list the first 6 terms of this sequence, Bn, and graph it. So that's the same thing. We're going to go ahead and just find Bn, B1, because we cannot divide by 0, so we should start with 1. But if we could, then we should start with 0. If 0 is not excluded, then that's what you should start with. So B1, B2, B3, B4, B5, and B6. Okay, so that is -1, exponent 1 plus 1 times 2 over 1. So that is 2. So -1 squared is 1. 2 over 1 is 2. So that's -1, 2 plus 1, 2 over 2 equals -1. Okay, that's -1 exponent 3 plus 1, 2 over 3. So that is positive 2/3. -1, 4 plus 1, 2 over 4 equals, that's -1 half. And then -1, 5 plus 1 times 2 over 5. So that equals 2/5. And last, -1, 6 plus 1, 2/6 equals -1/3. So we're going to try to graph it here. So we see the values. The values are for n equals 1. So we're going to have the points 1, 2, 2, -1, 3, 2/3, 4, -1/2, 5, 2/5, and then 6, -1/3, 1/3. So basically we're gonna start with x, n equal, so that's gonna be n equals 1, 1, 2, 2, -1, 3, 3 is 2/3, so that means 2/3 is 2 divided by 3 is 0.66. So 3, 0.66, let me put it here. And 4, -1/2. 4, -1/2. I'll put 4, -1/2 here. And 5, 2/5. 2/5. 0.4. 0.4. So that'd be somewhere here. 5, 2/5, and then 6, 1/3, -1/3, 6, -1/3, it will be somewhere here. So that would be the graph for this series. Here's another example. List the first 6 terms of the sequence Cn and graph it. For this one, I'm going to do the same thing. C1 equals 1/1, so 1. If it's odd, you use it to calculate it. You use 1/n to calculate the value, the term, and if it's even, you use the actual number for the for the uh, for the term. So C2 is even, so that's 2. C3 will be 1/3. C4 will be 4. C5 will be 1/5. And C6 will be 6. So to graph this, the other pairs will be 1, 1, 2, 2, 2, 3, 1/3, 4, 4, 5, 1/5, and 6, 6. So those are the points that we're going to graph. 1, 1, 2 2 3 1/3. 130 is 0.33, so 3 would be somewhere here. 1/3. 4 4. 5 1/5 be somewhere here. 2.2 and 6 6. So that's the graph for the series, the sequence C. In this, they want us to use the pattern to find the a few more terms. So it says use the provided pattern of each sequence to write their formula, then use your formula to determine the next two terms of each sequence. So in this next example, we have a few um, items that we want to find. First, find the pattern, right? Um, so use the pattern to find the formula that generates the terms. And then after you get the formula that generates the terms, then you can find a few more terms after that using the formula. But one thing that you need to know is that the terms of a sequence can be generated by two different definition of the sequence. But at least you need to look at the pattern and provide a formula that generated the terms that are already there and continues the pattern to give you similar terms based on the definition you give for your sequence. Let's look at the first example. The first example, what we see here is that there's exponential of the number e, right? But everything has denominator. But e is by itself. But what I can see is that's the first term that starts with e, or that starts with 1. So if we put 1 here over 1 to follow the pattern that you see the other ones are going with, so we would say that in this case, if we put a 1 as an exponent for e and 1 as the denominator for e, it's not changing the first term, but it makes it more obvious that if n equals 1, then you get e, right? So the second term of this would be e2 over 2. That means for n equals 1 here, and n equals 2 over here. And then it continues the pattern with e3 over 3, n equals 3. And it goes on to e4 over 4. So basically, when you're looking at this, you see that the pattern is going as taking the exponent of n and divide by n. So the expectation is that the fifth term will be e5 over 5, and the n term, the nth term will be en en over n. So for this one, we would say that's an equals en over n. And using that, if you plug in 5, you would find the fifth term would be e5 over 5 if you plug in 5, e5 over 5, and then since it says the two next terms, and then that's e6 over 6. So we found the pattern, and we found the general term, and we also find or the formula. We found the formula, and also we found the the next two terms for the first one. So that was A. Now let's work with B. B is 1, 1/3, 1/9, 1 over 27. Well, I see that this is going in a way where we getting some type of power of 3 in denominator, right? Some type of power of 3 in denominator. So the first one is 1 over. So what type of power of 3 you think that we can have on uh, um to get us to what type of power you expecting to have for 3 here to still have 1? You expect a 0, right? But what happens is when you have a 0, but the next term would be 1, is it 3? Well, it's 3. Yeah, that works, right? So then we keep on going. But if let's see if we go 1 over 3 exponent 1, right? And then 1 over 3 exponent 2, like this. Well, it seems to be working. So let's say it's n equals n, and let's continue with that. That's 1 over 3. So if we start with 0, n equals 0, that would work. But what if we don't want to start with 0? We just want to start with 1, right? If you want to start with 0, then your your formula would be, let me call it Bn. Let me put just the formula first. It would be 1 over 3 to the nth power, right? That's if you want to start with 0, right? But in case you want to start with 1, then you can just say that's 1 over 3 to the power n minus 1. Then 0 would not be able to be the first term because you would have a -1, n minus 1, so the power -1. Then you can start with 1. But if you want to start with 0, then you can have just that. You have two options in this case. You can have 1 over 3, or you can have also 1 over 3 to the power -1 n minus 1. Both of them. So this one starts with 0 or includes 0, and this one will start with 1. Okay. So, and then the two terms would be uh 1 over 3 to the power 4, which is 1 over 3 to the power 4, which is 1 over 81. And then the other term would be 1 over 3 to the power 5, which is 1 over, so 1, it's 3 to the power 5, 1 over 243. Okay, so the formula here is Bn, that is, I'm using 1 over 3 to the n minus 1, and then n would start, you would start taking values from -1, from 1. The next one is, B, is C, where you're getting only the odd numbers, right? So basically, the odd numbers can be generated by just going to use Cn. Now, how do you generate the n when n equals, so n equals 1, we want odd numbers, right? If n equals 1, you get 1. Now, how do you get 3? You need to find a formula that when you plug in a 1, it's still 1, and when you plug in 3, when you plug in 2, it gives you 3, right? You're gonna start thinking about that. When you plug in 2, you get 3. So when you plug in 1, you get 1. So if we have 2 minus 1, it's uh it's it's 1. So what if we do 2 times 1 minus 1? So that said n equals 1. Now when you do 2 times 2, n equals 2 minus 1, it's 3. When you do 2 times 3, it's 6, minus 1, it's 5. It looks like Cn will be Cn, the formula here would be Cn equals 2n minus 1, right? And then the expectation is that the other terms here, the two other terms, we have 7 should be 9, right? So that's for n equals 1, n equals 2, n equals 3, n equals 4. Now we're gonna do n equals 5. So that's going to be 2 times 5. So C5. 2 times 5 minus 1 is 9. Yes, that was the next uh, odd number. And then the next odd number after 9 will be 11. So C6 should be 2 times 6 minus 1. That is also 12. That is also 12 minus 1, 11. So these are the correct pattern. It keeps the pattern going. So the formula we had, 2n minus 1, kept the pattern going. So if you find another formula and that keeps the pattern going the same way it started, then that also can work. Next problem, D. We are looking for a pattern to get 1 when we square, 4 when we square, and so on. This one should looks easy. Dn would be n squared, right? And then the next ones would be 36 and 49 for n equals 1, 2, 3, 4, 5, and then 6, 7 for the next two terms. And then the last one, E, would be this example. But the first thing that you need to realize is that it alternates the sign. So you're going to need a -1 exponent. The signs alternate, right? Start with plus, then minus, then plus, then minus. So for the even term, for the odd terms, right? Start 1. The even terms are negative and the odd ones are positive. So that said, you're going to have n to the power -1, or n, because you want, when you have the odd term, the even terms, n minus 1. So if you have -1 to the power n, now when n is even, it will be, when n is even, it'll be positive. When n is odd, it will be negative, right? And you want it to be the opposite. You want it to be reversed. So that's why if you subtract 1, then it reverses it. Now, when n is odd, it will be positive. When n is even, it will be negative. So that's first thing that you want to realize. And after that, it's just 1 over n. Just 1 over n, because 1 over 1 will be 1. And when n equals 1, that's n equals 1, then it will be -1 exponent 0 times 1 over 1, right? So that's 1. For 2, it will be, for 2, it will be -1 exponent 2 minus 1, 2 minus 1, which will be 1, make it negative, and then times 1 over 2, so that's -1/2, and so on. So we can find that so En, it will be -1 to the power negative n minus 1 times 1 over n, and the other terms would be the two other terms would be uh 1 over 6 negative, and then 1 over 7. Okay, now let's talk about the factorial symbol. The factorial symbol is by definition, for n greater than 0, for n a number positive, not or 0, the factorial symbol n factorial, that's the symbol n factorial, the n with the exclamation point. In mathematics, it's read n factorial, or factorial of n. So is defined as follows. Factorial of 0 is 1. That's the definition. So whenever it's not 0, it's always 1. Factorial of 1 is 1. And for any other n that is greater than 2, So you're going to do n times the number next after n, and so on until you get to 1. You multiply them all. So if I'm looking for um, the factorial of 2, it's going to be 2 times 1, the number after it, or 1 factorial. It's 1. So that's why you can stop it at 1. So that's 2. So factorial of 2 is also 2, because factorial of 1 is 1. Now factorial of 3 is 3 times 2 times 1, which is 6. Factorial of 7 is 7 times 6 times 5 times 4 times 3 times 1 times 2 times 1. So that equals uh, that equals to 5040. And then factorial of 8 would be factorial of 8. Let me do factorial of 8 after we look at this property here, right? This property, what it tells you. It tells you when I'm looking for example, if I'm looking for factorial of 10, it's the same as 10 times factorial of 9. That's what this property says. So then since we already found factorial for 7, it's easy to find factorial of 8, because it's 8 times the factorial of 7, right? So which we already have, we can just multiply it by 8, then that is, the result is 40,320. Okay. Now let's talk about the recursive property of a sequence. So the recursive property of a sequence is when terms are being defined using other terms. So it's like you find the terms by using the prior term. So if I know the prior term, and I can find the term after it. So that's pretty much how the recursive property of a sequence is defined. So using the when you're using a term, the prior term, to get the next term in a sequence, you say that the sequence is recursively defined, because the terms are being connected to each other. Prior term gives you the next term. Here's an example. We have S1 equals 1, and Sn equals n times Sn minus 1. So if you have that, then you can find S2, right? It says find the 5 terms, the 5 first terms uh, of this recursively defined sequence. So S1 equals 1, then S2 by definition of Sn is 2 times S1, and Sn minus 1 is S2 minus 1. 2 minus 1, which is obviously S1. So 2S1. We know S1, right? S1 is 1. So 2 times 1 equals 2. Since we have S2, then we can find the next term, which is S3. S3, by definition of Sn, is 3 times S3 minus 1. 3 minus 1 is 2, so that's 3 times S2. S2, we found it, it was 2, so that's 3 times 2 equals 6. So we got S3 equals 6. S4 is, by definition of Sn, 4 times S4 minus 1, which is 4 times S3. S3 is 6, so 4 times 6 equals 24. We just found S4. S5 is, by definition of Sn, 5 times S5 minus 1. So that's 5 times the value of, let's say, S4. S4, we know it. We just calculated it. So that's 5 times the value of S4, that is 24. So that equals 5 times 24, 120. So we have the first terms of the 5 first terms of the recursively defined series. Here's another example. The 5 first terms of the recursively defined series. So we have you have u1, that is 1. Also, we have u2 equals 1. So we have 2 terms already. Now, we can use the definition of un to find the 3 other terms, right? So u3 will be, by definition, u3 minus 2 plus u3 minus 1. So u3 would be, that's u1 plus that's u2. So that means that equals 1 plus 1 equals 2. So u3, we found it, equals 2. By definition of un, u4 will be u4 minus 2 plus u4 minus 1. u4 will be equal to u2 minus plus u1, u3, sorry. We know u2 and we know u3, then you can find u4. u4 is, u2 is 1 plus u3 is 2, so that is 3. u4 equals 3. Let's find u5. u5 equals, by definition of un, u5 minus 2 plus u5 minus 1. So u5 equals u3 plus u4. And that is, u3 is 2, plus u4, that is 3. So that equals 5. So we found the 5 terms, first terms of this sequence. U1, U2, U3, U4, and U5. Now let's take a look at the summation sign. Summation sign is a condensed way to write a sum. So you see that sum here, and it follows a pattern where you can have 1, 2, 3, 4, and then you see the terms. You just add the terms. Well, we vary the numbers on the index for the numbers. That's the only thing that varies for the terms, right? So the fact that that's the only thing that varies, we use the symbol summation, the Greek letter sigma, which is an S in our alphabet. So the sigma is an S in our alphabet, is simply an instruction to sum or add up the terms. The integer k is called the index of the sum. It tells where to start the sum and where to end it. So look at this expression here. It says the sigma part is the S in our language, but it's a Greek symbol. Here is where you start. It says start at k equals 1 and end it at n. So every time you give k a value, it changes the term. So if k equals 1, that's the first term, plus the second term, that's when k equals 1, equals 2. Third term, that's when k equals 3, and so on. But it can tell you to start it at k equals 0, and k is the variable. You can name it however you want. You can say I as well, or you can say whatever. You can say t. So I equals 0 to n. That means you're starting at say ai. So that means you're starting at I equals 0. So the first term would be the a0 plus the second term, that's the one that's going to take the 1, and so on. So it depends on how they tell you to start and how you're going. Now let's look at these examples. We're going to expand those sums. So in A, it says expand the sum k equals 1 to n of 1 over k. Well, that's going to be 1 over 1, just 1, plus 1 over 2, plus 1 over 3. Well, we don't know where we're going to start because we don't know n. So we just add and then 1 over n. And for this one, for B, we're going to expand k equals 1 sum over k equals 1 to n of k factorial. So that will be 1 factorial plus 2 factorial plus 3 factorial plus so on and n factorial. It stops at n. It says write using the summation form. Well, it starts, well, it's the two, this doesn't vary, right? The square, it stays the same. The power doesn't vary. What varies is the feet, right? It starts from 1 squared, 2 squared, and 3 squared, and so on. It stops at 9. So it starts at k equals 1, and it stops at 9 of k to the power 2. So that's A. Pause the video and try this one. Well, it stops at n minus 1, right? So that's summation of k from 1 to n minus 1 or just n n minus 1 or n of 1 over 2 exponent k minus 1. When k equals 1, it's going to be 1 because that's 1 over 2 exponent 1 minus 1. 1 minus 1 is 0. So when k equals 1, it's going to be 1 over 2 exponent 1 minus 1. So that will be the 1. So that's the 1 we have, and so on. All right, so we have a few theorems using the notation properties, the summation notation property. So first thing, if you have a constant c, you can pull it out of the summation. If it doesn't, if the k that is varying does not affect something that is inside of the summation sum, then it can go out. So you see how the c here is, it's not affected by k, then you can move it to the outside. So any things that are affected by k can stay inside, should stay inside. But if you don't affect by k, by the variable, then you can be pulled outside of the sum and just multiply. If you have multiple terms affected by the variable k, then you can separate the sums. So summation k from k equals 1 to n of ak plus bk is summation of 1 k equals 1 to n of ak plus summation summation k from 1 from k equals 1 to k equals n of bk. And also same thing applies for the minus sign too. Also, if you have summation of k from, if you have a summation of k equals j plus 1 to n, where j is smaller than n but greater than 0, but integer, then you can have k equals 1. That means the from 1 to j, from 1 to j, k equals from 1 to j, from 1 to n, and take away from 1 to k to j, from 1 to n, and take away. So basically what you have is, say you have from 1, 2, 3, and so on j, and then j plus 1, j plus 2, and so on n, right? Now this part, these terms, we didn't need them, right? In the sum, we only started from here to say that's the sum from k equals j plus 1. We started here and we ended it here. All these terms, we did not want them, so that means we subtracted them. So that's why you have these ones, which is the part from 1 through j. You see, from 1 through j being subtracted, because this is only those terms. We did not need the terms that come before. So the whole thing will minus this part will be this. The whole thing, which is from k equals 1 to n, it will be the whole thing minus this will give you the part from j plus 1 to n. Okay, so well, also we know some of the sums that we will most likely use in problems. So if you add a constant n time, it equals the constant. So if you have sum from 1 to k to n, k varies from 1 to n of the same constant c, then it equals n times this constant. If you add k, the first n terms, right, of the set of integers, which is k equals 1 to n of k, which is 1 for the first term. The second term, k equals 2, k equals 3, and so on up to n. Well, it's going to equal to the n, the last term, times the last term plus 1 divided by 2. So that's a formula that we can use at any point, because this is um, really also demonstrated. So you can use it if you adding the first n terms, the first n integers, positive integers. Well, it's going to be the n times n plus 1 divided by 2. If you add the first n integers, positive integers, from 1 to n squared, k squared, sum of the k squared, that means 1 squared plus 2 squared plus 3 squared plus 5 squared plus so on, n squared, then here's what it equals to: n times n plus 1 times 2n plus 1 divided by 6. And also you have, and those are formulas to memorize too. So that is n, if you add the first cube, the first n integers cube, the first cube of the first n integers, the cube of the first n integers, the square of the first n integers, or the first n integers, then this one would be n times n plus 1 over 2 and then squared. So those are formulas to remember because you may want to use them at some point in exercise. So let's see if we can practice on this one here. So we can practice on the properties. A, we have the sum k equal from 1 to 5 of 3k, right? Well, we can pull the 3 out because it's constant. So that is 3 summation k from k equals 1 to 5 of k. Well, if we use this property here, so that's going to be that n, see, the first sum of the first 5 integers. It's going to be 5 times 5 plus 1 divided by 2. But we keep the multiplication by 3, so that's 5 times 5 plus 1 over 2. So that's 5 times 5 plus 1, 6, 30 over 3, and then times the 3 over 2. So that's 3 times 15, and that is 45. So summation of k from 1 to 5 of 3k is 45. Also, what you could do too is you could expand it and see if the formula works. But I do know the formula works. So if you want to verify, you can just add them and multiply by 3. I'm just going to do it for this one, but the rest you should believe that the formula works. Because so we have sum k from 1 to 5 of 3k, right? So that's going to be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5, right? So that is 3 plus 6 plus 9 plus 12 plus 15. That's 9, 18 plus 12 plus 15. That's 30 plus 15. That is 45. Okay. Just wanted you to verify this. So that works. Next, they say to calculate this, sum from k to equals 1 to 10 of k. So we can break it down, give each part their sum. So k3 plus sum k equals 1 to 10 of 1. 1 being a constant. Now remember we said here, if you sum a constant n times, it's n times the constant, right? So then this one will be 1 times 10, that's 10. And this one is k cubed from 1 to 10. So 10, k cubed from 1 to 10, that's the 10, and then divided by 2. 10 plus 1 divided by 2, then square. So that is, let me pull it here. Let me put it here. So that's 10 times 10 plus 1 over 2 squared, and then plus 10, right? So that is 5. I divide the first 10 by 2. 5 times 11 squared plus 10. So that is 55 squared plus 10. So that is 55 squared plus 10. That's 3,035. So that's B. C. C is summation K from over K equals 1 to 24 of, we can separate each. So that's K squared minus 7. I can pull the 7 out. K1 to 24 of K, and then plus K summation K1 to 24 of 2. The last one is a constant. It's going to be the constant times n. N is 24. So that's 48. 2 times 24. So let me write it down. So this would be, the formula for square is this, right? So that's n factor 20. N is 24. So 24 factor 24 plus 1 plus 2 times 24 plus 1 divided by 6. So that's 24 factor 24 plus 1 times 2 times 24 plus 1 over 6. The next one is K, which is this. So 24 times 24 plus 1 over 2 minus 7 times 24 times 24 plus 1 over 2. And then last one plus 2 times 24. Because when it's a constant, you just multiply the constant by n. Now we can divide 24 divided by 6 is 4. So that will be 4 times 25 times 49, right? That's 24 times 2, 48 plus 1, 49. Because we divided by 6, we divided 24 by 6. And this one will be negative 7. 24 divided by 2 is 12 times 12 times 25, and then plus 48, this one. Now we're going to finish this using your graphing calculators. That's 4 times 25 times 49 minus 7 times 12 times 25 and plus 48. So that's 28, 2,848. So basically we have this equal to whatever the problem was. It was summation K equals 1 to 24 of K squared minus 7K minus 7k plus 2. So that equals to 2,848. And then last, D, summation k equals 6 to 20 of 4k squared. All right, so basically, we also know that that k k uh from 6 to 20 is equal to summation k from 1 to 20 waves. From we know that this is using this property right here, 1 to n minus 1 to j, right? So the j is 6, so that's going to be summation k from 1 to n 20 of 4k squared minus summation from 1 k equals 1 to 6 of the same expression. We don't want the 4k squared here, of 4k squared. So when we take away this part from that, it gives you this. So then this would be, this is 4 summation k equals 1 to 20 of k squared minus 4 summation k equals 1 to 6 of k squared. And then we can use the formula here, this formula, that one, with 6, n equals 6 and n equals 4 for each of these. So that's 4 times 20, where n equals 20 and equals 6. For n equals 20 in this one, 20 times 21 times 2 times 20, 41 over 6. And then we would minus 4 times 6 times 7 times 2 times 7, 14 plus 1, 15 over 6. We can cancel the 6 here, and we would go ahead and do this one and this one with the 6 canceled. Then we'll get the answer. So that is 4 times 20 times 21 times 41 divided by 6 minus 4 times 7 times 15. It equals to 11,060. So that's the sum from k equals 6 to 20 of 4k squared. That gives me 11,000 um oh wait, there's a problem here because I think that's 6. That's not 7, that's 6. So that should be that should be 7 times, well, let me look at that again. So that's so that should be 5 because we stopped at 6. So 5. So we got from, because 6 is already included in here. So that would be k from k equals 6 to 20. And k equals 1 to 20. And then we got 5 left because you got 1, 2, 3, 4, 5, and 6. Blah, 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 20. Right? We take these ones, that's the ones we are calculating for, and then we are subtracting this one. So from 1 to 5 is subtracted. From 1 to 5. From 1 to 5 is subtracted. And then now it changes the whole thing here. We're going to have this one cancels out, this one also. Well, everything else looks good. It's just that we're going to have uh 5 5 6 and 2 times 5, 10 plus 1. Well, basically you have 5 plus 1 and 2 times 5 plus 1, right? So that's 5, 6, and 11. Okay, so that will be 4 times 20 times 21 times 41 divided by 6. And then you also will have minus 4 times 6 times 11 divided by 6. 5, 4 times 5 times 6 times 11 divided by 6. So the result is 11,260. And